What's up, everybody? Today we are going to talk about DGK iteration, and it's a type of solution method for the mu synthesis problem. And in the previous video, we talk about DK iteration, right? And it's kind of the advanced version of it. But when I say advanced, I don't mean it would give you better performance or something. It is being used for other types of problems. What do I mean by other types of problems? Let's start from scratch, right? This is, let me get another color. This is where we start our problem, right? And we have constructed our perturbation here. This is our perturbation, and most of the time, let's say it can be the perturbation always, or the entries of the perturbation can either be zeros or complex numbers, right? We don't necessarily consider them as being real, right? And if all your perturbations can be considered as complex numbers, you will directly use DK iteration. Okay, and we talk about this in the previous video, right? However, if you are only concerning yourself with some specific parameter that you know for sure that it's real, right? And then you would use DGK iteration because it would give you less conservative controller, meaning a controller with a better performance, right? Okay, so now I'm going to start talking about DGK iteration, and there are like a couple of steps to that. In general, though, the idea is like simple, or rather similar to the DK iteration. And if you watched the previous video, you are going to notice the similarity. All right, so this is our problem. However, delta, the perturbation can be such that P1 or P2, right? And some other complex perturbations, let's call it delta 1. And here, P1, and also let's call it PI. P1 and PI, they are real numbers, okay? And for that type of problem, you can use DK iteration, but it would give you, or rather, DGK iteration would give you less conservative results. All right, we established that. And okay, I just want to, and also, you know, there is a structure to that. There is a structure to the perturbation that you have. Okay, so another issue. Let me maybe delete that. All right. Okay, or maybe not. Okay. All right. In the first step, as in the DK iteration, you will just ignore perturbation, right? Just look at this. Look at this part. You would ignore perturbation, and you would state the K part of it, K part of DG hyphen K, right? Iteration, the K and DG part of it. And in the K part, you would just ignore perturbation and then formulate your problem here in that way, in that form. And this is H infinity framework. You would design this K, right, such that the gain from, or the transfer, H infinity norm of the transfer function matrix from exogenous input signals to Z regulated output is minimized. Okay. All right. So now we know what K is, right? And again, this is mu synthesis, so I mean, I'm just directly stating that as delta perturbation, but it has some structure, right? Just wanted to make that clear. Okay, maybe make it like that. Okay, so now we know what K is, right? And then now we are going to focus on DG part of it. We completed the K part, and now we are going to focus on DG part, right? And we are going to switch between those stages till the convergence, right? Okay, so we know this, right? And then just using lower linear fractional transformation, right? And we have this now. By the way, we know what n is, right? And now, as in the DK iteration case, we just represent the problem by assuming, right? By assuming the relationship between W and Z, right, as a perturbation. Okay. Perturbation satisfying some constraints. It needs to satisfy some constraints. Okay. And here, let's look at this. N of S is N of S, right? And like in the previous part, we have some frequency, this kind of quantization, right? And for each frequency, let's call it omega 1, right? Omega 1, maybe 0.0001 radian per second, right? And okay, n is a, and let's call it for omega 1, right? Becomes n1. n1 is just a n by n complex matrix. Okay. For that, now we are going to find D and G complex matrices, right? And now we are going to look at how we would find that. I'm not going to go into the details, right? I was planning on going to into the details. However, after I'm more familiar with the by reading Young 1993 Caltech thesis, right? And I kind of seen the depth of the this problem and the solution. So I'm like really scared. So I don't think I will do more detailed explanation on that than this. I feel like, all right, so this is the problem that we need to solve for each omega, right, frequency value. And just want to state something obvious. If we need to find D and G, right? Okay, and here look at this. If we assume G is 0, by the way, that would be the case if we didn't have any real perturbation, right, entry in the delta block, we would have the same kind of optimization problem when we look at the DK iteration part, right? So it's very similar. And okay, here we are just bisecting, right, gamma, and this is linear, right? Linear in if we fix omega, right? And this is how we would solve that, by the way, right? We would like epsilon or something, and then 1000 maybe, and then we would bisect gamma, right? And we will say, hey, gamma is 10. Find me G and D. Is it feasible? If yes, okay, then lower gamma. That's the kind of process. And for fixed gamma, look at this. D is linear, right? G linear, again G linear, and M is like linear, right? So this is something that can be solved by using typical LMI methods, right? And okay, so in DK iteration, the D part of it, we determine for each frequency D matrices, right? the better way of stating that, d omega, right? D omega. We found d omegas, and now on top of d omegas, we also have g omegas, right? And as in the previous video in DGK iteration, when we have d omega, we need to find d of s, right? And it's like the same kind of logic that you use when you have a bunch of data and you wanna find a function that can be linear, non-linear, but you have the form of it. It's like curve fitting, right? Okay, it's like the curve fitting of transfer function version of it, right? So, however, it's not like straightforward curve fitting. You also have some additional constraints, right? And let's look at those additional constraints. And so this, I just took this part directly from the thesis, right? Yeah, let me write this again. Young, 1993, Caltech thesis. And please check the link down in the description, right? I added that, and through that link you can just download this PDF file from the Caltech library or something, and you can just look at the document. All right. So first, just find d omega and g omega by solving iteratively for each omega, solving the given this given problem. Okay. All right. And in the second step, find d of s and g of s, like curve fitting, I said, right? This process is not detailed here. I mean, due to the fact that it includes some numerical subtleties, and I don't have the background, right, for that. And okay, in the third step, let's say after we have d omega and g omega, we have a magic way of finding d of s and g of s. Let's take it for granted, okay? This is for computer engineers or maybe numerical people are for, right? Okay, so division of labels 101. And in the third step, replace d and g. Yeah, we need to also do pre-processing for d and g, right? And with quote unquote appropriate vectors, and that kind of requires some asterisks, right, and additional information. However, for example, what was the constraint in DK iteration for d? In the d part, when we have d omega, we need to find d of s such that d of s is stable and minimum phase, right? Okay, so in that kind of right, similar to that, we also have these four, I guess, transfer functions being stable constraint. And in addition to that, yeah, this symbol, this like tilde, right, it is the conjugate of a system, right? So let me just a quick example. Let's T of S is 1 over, right? And let's, okay, so T conjugate is just substitute with minus S and transpose it, right? S, maybe. Okay, 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 1 over S. All right, that was not a good example because it didn't like highlight the fact that okay, okay, so this is conjugate of T and this is T, right? We just switch S with minus S and then take the transpose of it, right? So that's the logic here. So let me delete that to have more space. And okay, so there are constraints, and this is constraint 1 and this is constraint 2. I guess it's not like that, just this is the constraint, right? And this is the definition of GH. GH is the spectral factorization of G such that this equality holds, right? And I hope in the future I have some ideas about that, doing some additional tutorial videos about spectral factorization, copolyne factorization, inner outer factorization. I have some ideas about that, especially by using like state space representation and also LMI procedures, right? Just determining the spectral factorization and using like YOMIP or something. Okay, so and then okay, just let me draw a line here and augment D and GH with identity matrices. Okay, I mean it's not hard, right? D and G, just identity. All right, okay, and you can kind of get that just for the dimensional agreement with the P. All right, and in addition to that, augment G with zeros, so they're compatible with D. Okay, it kind of again like there is a similarity to DK iteration. Okay, so in the fourth step, form the state space system, right? Form the state space system P sub DG, P DG, right? And again, I'm not going into the details of it, right? Even though I don't go to the details, the lecture time is like not short at all. And for that new system, just design. Again, you know what PDG is, right? At this stage, yeah, it's like this, and you know what G, GH, the spectral factorization of it, and D, right? And you also have P and gamma star. Gamma star is like the number, like the mu value, right? The maximum mu value, and okay, we determine mu. I'm sorry. Okay, gamma for each frequency. However, we take the maximum of it and we call it gamma star, right? So in each omega, we computed the gamma, right? But let's call it like really close to 0 radian per second. But the maximum is what we use here. Okay, so all right, and now we need to determine k by using h, by minimizing the h infinity norm of the tz omega tzw, right? And if you wanna represent the PDG in a more, I guess, block diagrammatical way, here is the figure that's being used in the Young's thesis, right? And so you find k, and then you just iterate the process. And here again, this is the D part of DK iteration, right? Just I want you to focus on, I guess, this part, right? Okay. We have talked about that in the previous video, and before saying that, I just wanted to make something another clear. You don't, for example, you have a given. Let's check this part. Let's check this part. Right? You have a given perturbation. Right? And here, P1 is real number, right? And again, P2 is like that, P3, and delta 1 is complex number, right? Only scalar. Delta 2 here, delta 2, but identity. So it's a repeating diagonal form, right? And again, some delta 1, full subblock, right? Complex. If you have that, using some rules, we have talked about this in the previous videos, right? You just directly determine the, I guess, structure of D, or you can parameterize your D matrix just using the rules in the video, right? And whenever you have some scalar times identity, and even the only scalar is like scalar times identity but dimension 1, right? Is like that. You can just write d1, you can just write a d scalar term, okay? And so d term, and now I'm looking at this. Yeah, I mean, just for this p1 we have d1, right? And for this p2 we have d2, and d1 and d2, due to the dimensional reasons, this is like 1 by 1, and d1 is 1 by 1, right? And okay, here let's look at this. p3 times identity, again this is 2 by 2 but full, like, I mean 2 by 2 complex, right? It's not diagonal or something, or scale. D3 is not scalar. D3 is a 2 by 2 matrix, full matrix, right? So it's not like D3 times identity. It's like 2 by 2 full matrix, right? Okay. And here for this, again, we have D4. This is 1 by 1, and again D4 is 1 by 1. And for that, we have D5, and this is like the dimension 3, right? And this is 3 by 3 matrix, right? And for that, this is 2 by 2 full perturbation, right? And for that type of, I mean, I'm just directly using the rules that I mentioned in the like previous video, I guess, right? And this is some scalar times identity, such that it's like 2 by 2. Okay. And again, D is Hermitian and positive definite. And for example, D1 is a scalar and it needs to be Hermitian, so it's real, right? Okay, so just implicitly it is real. And since we have like the real section and also the complex section, right, we are only focusing on the real part of our perturbation when we are constructing our G matrix. And here again, just doing the same thing, right? G1, G2, and G4 for each like subblock, okay? And however, this G1, G2, and G4, you can just consider them as Hermitian. Wait a minute, is that correct? I'm feeling a little doubt about this. It may not be correct. Wait a sec. I feel like I need to check this. Sec. Okay, never works when you need that to work. Yeah, I'm looking at this. Yeah, it needs to be, yeah, okay, it needs to be Hermitian. Okay, that's all right. It's correct. It needs to be Hermitian and complex, right? Okay. So for example, G3 is 2 by 2 Hermitian matrix, but D1 is D3 rather is again 2 by 2 complex, and G is only Hermitian, but D is Hermitian on also on top of being positive definite. Okay, so that's the parameterization of how you would parameterize D and G. Okay, so when you are using this formula to solve that, you also need to impose that parameterization kind of constraints on D and G decision variables, right? Okay, well, just wanted to make this clear. In the future, I'm going to make some MATLAB and YOLMIF videos on H infinity, right? Design, and maybe more about mu synthesis, right? And hopefully in 2022, right? It's my New Year's resolution, I guess. I wanna make some nonlinear contour by using H infinity or mu synthesis. Okay, just wanted to represent the nonlinearity by some, of course, sector, it must be sector kind of nonlinearity by again perturbation block, and then using H infinity, right, or maybe mu synthesis type of solution methods. And I like to make it, stable and also kind of optimal, right? And maybe in this year we're going to see that. And it's December 29, right?